Hello. In this segment, we're going to talk about RISC versus CISC. Let's start out with some definitions. CISC is a complex instruction set computer, whereas RISC is a reduced instruction set computer. Both of these different architectures evolved at different points in history, so let's look at a little history. The motivation for complex instruction set computers were that early computers had very little memory, and that memory was comparatively slow. So, if we could fetch fewer instructions from memory, then the computer could be faster. So the general characteristics then for complex instruction set computers are that there are a large number of operations. The assembly language has 300 plus mnemonics that we would find. And therefore, compilers have less work to do to translate a higher level language into machine code because there are more choices for the instructions that it's generating. There are also a large number of instruction formats, perhaps dozens of instruction formats. And these formats are of varying lengths, from say 1 to 15 bytes in length. More than that, some of these instructions take very few clock cycles and some take many clock cycles. There were generally fewer registers and more memory accesses in the complex instruction sets. And because of this, the complexity of the CPU means that there were a large number of transistors on the CPU and therefore higher CPU prices. On the other hand, RISC came out of the growth in quantity and quality of memory. As memory capacities grew, there was less need to have a lot of code packed into a small space. Also, it was getting very difficult to push the clock rates higher and higher and higher on the complex hardware. So a simpler processor could run faster. The general characteristics then for RISC are that there are a lower number of operations, only about 150 opcodes in the assembly language. And so compilers are going to have more work to do to translate a high-level language into the machine code because of the fewer choices of operands. Also, there were a small number of instruction formats, maybe 5. And all of these instruction formats were of a fixed length of, say, 32 bits in length. But the advantage is that all instructions take exactly one cycle to execute on the processor. This is also a load-store architecture, meaning that only the instructions load and store could actually go out to memory. If you were going to add, subtract, multiply, or divide, those operands had to come from existing registers. So because of this simplicity of the processor, there were a smaller number of transistors, lower CPU complexity, and therefore these were less expensive processors. If we want to compare the performance of RISC versus CISC computing, the equation is exactly the same. The amount of time that it takes for a program to execute is equal to the amount of time for a single clock cycle times the average number of cycles that it takes for an instruction times the number of instructions for a program. That gives you the time for the program. RISC tries to minimize the number of cycles per instruction, one cycle per instruction, whereas CISC tries to minimize the number of instructions per program, whereas RISC, on the other hand, the programs were much, much larger in machine code. But it turned out that compilers followed the 80-20 rule even for CISC architectures, that even though they had a large number of choices for their instructions, turned out that 80% of the time they only needed 20% of the instructions, and this made a good case for RISC. Today, RISC performs better and costs less. CISC adapted to the increased performance of RISC by adding even more hardware that actually decodes most complex instructions into much smaller RISC-like instructions that actually execute. This is called code morphing. Market factors, though, keep complex instruction set computers alive, such as the Intel architecture, because of the wealth of software that's available for them. RISC has rapidly gained a lot of market share today, mostly due to mobile processing. The ARM processors that are in most mobile phones today are RISC-based. ARM stands for the Advanced RISC Machines. And because they are simpler, they consume less power, which extends battery life. In summary, CISC processors require more CPU transistors in an effort to maximize the density of code in memory. RISC processors, on the other hand, use a simpler design in an effort to reduce the number of cycles that it takes to execute a single instruction. The only major CISC architecture today is that of the Intel x86 and 64, and nearly everything else is RISC-based.